Let's talk about organic chemistry. This is kind of going to be an initial overview. So first, all about carbon. Well, organic literally means it contains carbon, but specifically, for the most part, it is carbon bonded to hydrogen. Okay, so just having carbon isn't enough. In almost all cases, it is carbon bonded to hydrogen. When might it be different? When it is a carbon bonded to all halogens. Sometimes that is going to fall into the category of organic, but let's just think a general rule. Organic means contains carbon, and specifically carbon bonded to hydrogen. Some specific compounds to remember that they are not organic. Now, if you remember that carbon pretty much needs to be bonded to hydrogen, then this will make sense. So carbon dioxide, which is carbon with 2 oxygens, and carbon monoxide, which is carbon with 1 oxygen, are not organic. They are called inorganic. They are not organic. So remember, carbon forms 4 bonds, but those bonds do not all have to be single bonds. What it means is that everywhere you find a carbon atom, you should count around and find 4 bonds. So right here is a carbon atom, right? 1, 2, 3, 4. 2 sets of double bonds, okay? Here is a carbon atom right here, and we have 1, 2, 3, 4 bonds, all single bonds. So look over here. Every carbon has 4 bonds around it. Okay. It does not have to be a single bond. Could be a double or a triple, but the total number of bonds must be 4. Okay. Just to reiterate, carbon can form single bonds, double bonds, and triple bonds. And this is part of the reason that carbon is just an extraordinary compound and essential for life. Carbon is super unique. It can form long chains, think like DNA long, like huge, okay? It can form short chains. It can form branched chains. So we have a chain with some branches coming off, one or many. It can form rings. So carbon is super unique. Something to remember, each bond is 1 pair or 2 electrons that are being shared. So in a single bond, it's 2 electrons or 1 pair shared. In a double bond, it is 4 electrons or 2 pairs. In a triple bond, it is 6 electrons or 3 pairs. That is important to notice and pay attention to the language. Are they talking about total electrons or are they talking about pairs of electrons? Be careful. Let's talk about hydrocarbons. Hydrocarbons are essentially the simplest organic compounds. They contain, not surprisingly, only hydrogen and carbon because they are hydrocarbons, hydrogen and carbon. So sometimes you'll see a question like this: which structural formula correctly represents a hydrocarbon molecule? Now I can tell this has oxygen, so I know that's a wrong answer, so I don't want to pick that one. Now I'm stuck and I'm like, wait a second, the rest are all hydrocarbons. So it says correctly. Do you remember how many bonds carbon had to have around it? 4, right? So let's look at this carbon right here. It has 1, 2, 3, 4, 5. Eek! Let's look at this carbon. It has 1, 2, 3. Eek! Let's look at this carbon. 1, 2, 3, 4. Phew! There we go. Now for naming hydrocarbons, you use table P. Table P is organic prefixes. It tells you the number of carbons in the chain, okay? So part of that means finding the longest chain, okay? So essentially I'm going to look where carbon is connected to carbon, connected to carbon, connected to carbon, and I'm going to find the longest chain I have. Now here, all of the carbons in this molecule are all in one chain. So I'm only going to see 1 carbon prefix in the name. So how many carbons are all connected 1 to 1 to 1 to 1 to 1? It is 7. So the name of this will use the prefix het. Now for this one, it's a little bit more complicated, okay? Why? Because I can go like this for my chain, right? I could go like this for my chain, or I could go like this for my chain. What I want to do is find the largest number of carbons connected in a chain. And to make it easy, I'm going to use the straight line unless I need to curve it, to branch it. Okay, so in this case, it's just those. So how many carbons are in that longest chain? Well, it's 5. So the name of this carbon molecule will use pent, but there's also a branch. So you see this? That's not part of the chain. That carbon is like off. Okay. How many carbons are in that branch? 1. So what does that mean? That means the name of this compound will use the prefix pent when talking about the chain and meth when talking about the branch. All right, here's another one. How many carbons are in the longest chain? Can you figure it out? See all the ways that you can go carbon to carbon to carbon to carbon. Can you go this way? Can you go this way? And if going straight across works, we'll do that. But if it doesn't, we'll have to go another way. Yeah, going straight across works because all the other ways still make the same number. So how many carbons are in that chain? 5. So the name of this will use pent. But then where's the branch? There's the branch. Those 2 carbons in that branch are not part of the chain. So how many carbons are there? 2. So the name of this compound will use pent when talking about the chain and eth when talking about the branch. So saturated versus unsaturated. Here is an illustration of a saturated hydrocarbon and an unsaturated hydrocarbon. What do you think it means? Well, saturated means they're all single carbon-carbon bonds. It's full of hydrogen. Each carbon is holding as many hydrogens as it is allowed in terms of bonds. So this end carbon will have 3. This end carbon will have 3. And all carbons in the middle will have 2. Okay. If there is a branch, still when we're looking at carbon to carbon, each carbon, unless it is a bond with carbon, is filled with all the remaining spots with hydrogen. Now, when something is unsaturated, it has at least one multiple carbon-carbon bond. What does that mean? A double bond or a triple bond. So remember, the end carbon should be full of 3 hydrogens, right? Well, here's an end carbon, and it only has 2 hydrogens. Why? Because it has this double bond, and carbon can only form 4. So this is unsaturated because each carbon is not filled with the maximum number of hydrogens because there's a multiple bond. Which of these is a saturated hydrocarbon? What does saturated mean? Each carbon is filled with as many hydrogens as possible, so there will only be single carbon-carbon bonds. Yeah, there we go. Now, there are special names for hydrocarbons. So what do you notice here when we're naming? What are some things that you notice? So let's look at it on table Q. This reference table will help you. What do you notice here? Okay, because the chart that I just showed you, that's not available to you on the exam, but this one is. So what do you notice about this? So let's get specific. What do you notice about the names? Well, the names, when the homologous series is alkanes, it ends in A-N-E. When it is alkenes, it ends in E-N-E. When it is alkyne with a Y, it ends in Y-N-E. right? So we notice that about the names. And that is right here. So it's alkanes, A-N-E. Okay. Now let's check the math because we see some general formulas here. Okay. So let's check. Okay. So here are all alkanes. Okay. And we see the general formula is CnH2n plus 2. What that means is once I know how many carbons I have, I plug that number over here, and I should be able to do that simple algebra to find the number of hydrogens. So methane has how many carbons? 1. So then I do 2 times 1 plus 2. 2 times 1 is 2 plus 2 is 4. Aha. Let's check ethane. Ethane has 2 carbons. So using this formula, 2 times the number of carbons plus 2. 2 times 2 is 4 plus 2 is 6. Okay. Now let's look at propane. 3 is the number of carbons using this same formula. 2 times 3 plus 2. 2 times 3 is 6 plus 2 is 8. And let's just look one more using this formula for butane. 2 times 4, the number of carbons, plus 2. 2 times 4 is 8, plus 2 is 10. So essentially what you do is you double the number of carbons and add 2. Double the number of carbons and add 2. How many electrons are shared in each single bond? Let's just refresh. Yeah, 2 electrons or 1 pair, right? All right, now let's look at alkenes and check the math. Okay, so alkenes has a different formula, right? Just CnH2n. So I added 2 last time. With alkanes, I don't do that. I just double the number of carbons. So ethene has how many carbons? 2. Double it, 4 hydrogens. Propene has how many carbons? 3. Double it, it has 6 hydrogens. Butane has how many carbons? 4. Double it, 8 hydrogens. And if we counted them in each of these, we would see them. As a reminder, how many electron pairs are shared in each double bond? 2 pairs. All right, now let's look at the math of alkynes and check this. Okay, alkynes uses this formula, right? So almost the same as the other ones, right? But this time, instead of adding 2 at the end, I subtract 2. So let's check it. For ethene, how many carbons? 2. So I have C2, right? And for hydrogens, I would do 2 times 2 minus 2. So 2 times 2 is 4, minus 2 is 2. Is that what I have? Sure is. Let's check this one. How many carbons? 3. So how many hydrogens would I expect? I do 2 times 3, which is 6, minus 2 is 4. Is that what I see? Yep, sure is. And then let's look at butane. C4, H, how many? I'll use this formula. 2 times 4 is 8, minus 2 is 6. And is that what I see? Yep, sure is. How many electrons are shared in each triple bond? 6 electrons. So see, you just got to be careful, right? Is it pairs they're asking me about, or is it electrons? Again, here, what do you notice about butane, 1 butene, 1 butane? Okay, so let's look at butane, all single bonds. But then we look here and wait a second. Why do I have numbers? Okay, well, I know it's butene because I have a double bond, and it's butane because I have a triple bond. Why do I have a number? What would I need the number for? Do you have an idea? All right, let's maybe look at another example and see if you can notice. So here, these are both butane. You can see Y and E. They have triple bonds, but this has an address. That's what I call the number in front, the address of 1, and this has an address of 2. So what changed? Why would it be 1 butane versus 2 butane? If you guess that it had to do with the number, the carbon number that the bond is attached to, you would be right. So I could number the carbon chain like this. I could also number the carbon chain going in reverse, because there's no rule that says I have to go this way, because I could literally just, okay? So what I'm going to look for is find where the triple bond is, okay? And what is the lowest number carbon it is attached to? 1. Here, I'm going to do the same thing. I number the chain going forward, and then I number the chain going reverse. Find the triple bond, and what is the lowest number that it's attached to? It's 2. This leads us into isomers. So isomers are substances that have the same molecular formula, but different structural formulas. And for organic chemistry, the way we know that is they have different names, okay? So these are both C4H10, but look at these structures, different, names, different. As in organic chemistry, we name them based on their structures. Here we have also isomers. If you counted each of these, we have 5 carbons and 10 hydrogens in all of these, but different structures, different names. But the definition doesn't have to do with the name. That's just a way that we can remember. So what are isomers again? They are substances with the same molecular formula, but different structural formulas. Okay. Now, they have different properties because of the different structures. We should remember this. Different structures equals different properties. So just to give you an example, butane, which you see here, smells a little bit like gasoline, and it has a boiling point of 274 Kelvin. But 2-methylpropane, which is also C4H10, but a different structure, is odorless, and its boiling point is a little lower. So different structures yields different properties. So isomers are substances that have the same molecular formula, but different structural formulas. And because they have different structural formulas, they have different properties. Now, these two are not isomers. Do you know why? Well, they don't have the same molecular formula. So they both have 4 carbons, but this one has more hydrogens, so they are not isomers. So one way you can kind of tell if 2 compounds are isomers is to kind of go through this flow chart in your brain. So you look at them. Do they have the same molecular formula? If the answer is no, or the answer is yes. If the answer is no, it's simple. They're not isomers. Okay. If the answer is yes, they have the same molecular formula, then I have to go further. Do they have the same name? Like, would they both be 1-butene? Okay. If the answer is yes, or the answer is no. If the answer is yes, they're not isomers. 1-butene and 1-butene are not isomers. They're literally the same thing. But if they do not have the same name, then they are isomers. Okay, an easy way to draw an isomer is to remove 1 carbon from the chain and make it be a branch. So that means you take it off the end and move it somewhere in the middle. So for example, this carbon chain has 6 carbons in it. I'm going to take one of them off the end and move it somewhere in the middle, like this. Okay, so the name of this would just be hexane, right? That's hexane. It's just 6 carbons in a chain, no double or triple bonds. This one, now there's only 5 carbons in the chain. The branch has 1. 5 carbons in the chain. The branch has 1. okay? And this indicates the address the carbon number is attached to, the lowest number possible, okay? So it's the easiest way to make an isomer. So when we look at this one, how could we draw an isomer? Well, let's look. How many carbons are in the chain? 5. So let's make it one shorter. 1, 2, 3, 4. But I can't make that carbon disappear because remember they need the same molecular formula. And I got to take that carbon and put it on one of the middle ones. It doesn't matter which one, but I can't just put it on the end because that literally just keeps the chain. So I'm going to put that one carbon I took off right here. And then I'm going to add lines to indicate each bond where there would be a hydrogen on the end, making sure that each carbon has 4 bonds around it. Now, fun fact, see how these hydrogens are all drawn? When you're doing this on the test or an exam, you don't need to draw those hydrogens. It is assumed if there is a line at the other end will be a hydrogen. You could draw them, but you don't need to. All right, so what would the name of this be? What is the longest chain? Bute. No double bonds or triple bonds, so butane. Okay, but I have a branch. How many carbons are in the branch? 1. The prefix for 1 is meth. YL means it's a branch, like ein, ein means a chain. YL means branch. The last thing I need is an address, like where did you put it? Okay, so you number the carbons this way, and then you number the carbons going this way, then you number the carbons going this way. This branch right here is attached to the lowest number carbon when it's a 2. So this would be 2-methyl butane. That is organic chemistry.